Okay, so now I'm recording. So the assumptions are the universe is homogeneous and isotropic, and there are, sorry about the question marks, there are three maximally symmetric three spaces: the Euclidean three space, the surface of the three sphere, so the surface of a sphere in four space dimensions, but that sphere in four space dimensions is a three-dimensional surface, so that's one, that's the model of a closed universe. And then there is the three-dimensional hyperboloid, which is a which can be embedded in a four-dimensional space-time. Anyway, these are the three maximally symmetric three spaces. And what we do is what Robinson and Walker quite brilliantly did so long ago was to say that our universe being homogeneous and isotropic, the space part must be a maximally symmetric three space. So it's one of these three, and then they added in time as a scale factor. So time enters simply as the scale factor that expands one of the three maximally symmetric three spaces from the tiny Big Bang to the present very large size. The astronomers somewhat, I think, absurdly use the scale factor as 1 at the present time. I think that's pretty weird, but that's what they do. So I'll go along with that, although if I were running the show from scratch, I would not do that. So what we've got then as the invariant then is minus c squared dt squared. So this is the invariant distance when a little bit of time goes by. Then the distance between points separated by dr, d theta, and d phi then is given by this, stretched by the scale factor a of t. And so the metric has this very simple diagonal form. And this constant L, what is L? L, most people don't put in L because they want to be sophisticated and so forth. If R is a distance, then and K is dimensionless, then we've got to put in an L. L is basically the size. If the universe is compact, then L is the spatially compact. Then L is the size of the universe. If L is infinite, then L is just a scale factor that goes in here to make this dimensionless. So this is the metric then of space-time, and in order to apply Einstein's equations, and remember, what are Einstein's equations? Well, they are basically that, well, in fact, they just relate Rij and R, the Ricci tensor and the curvature tensor, to the energy momentum tensor T, and the Ricci tensor and the Riemann scalar are given in terms of the Christoffel symbols of the second kind and their derivatives. And the Christoffel symbols of the second kind are given by the inverse metric. And notice the inverse metric is very simple to calculate because the metric is diagonal. And then they're given by derivatives of the metric. So at first, in fact, it's very simple conceptually, but there are all these indices that go from 1 to 4 or 0 to 3, or from T to phi. And so we've got things that are quite complicated. On the other hand, because the metric is so very simple, it depends only upon r and theta and t, although the t dependence is hidden. It's a squared of a of t squared. And so Gij, comma k vanishes. Well, now that I think about it, the Gik squared does not, I just did this afternoon, and now what I realize is that I forgot to differentiate A with respect to time. And so there's G00, comma 0. In fact, all the G's, comma 0 are not 0. So I will fix this before I post it on the class website tonight. But one can compute the other ones, GRR, comma R, G theta theta, comma R, G phi phi, comma R, and G phi phi, comma theta. And to make up for my, now let's see, what do we have to do to get this? Oh God, I want to write on this screen for you. Tap to connect. So I tapped, presumably I can, whoops, connect now. But first, okay, so let me do some of these derivatives. G00, comma I is just 0 because G00 is just a constant. But GRR, comma 0, well, that's going to be 2A dot over 1 minus k r squared over L squared. Here we're assuming that T, the independent coordinates are T, R, theta, and phi. And G theta theta, comma 0, well, this is also going to be 2A dot, but now it's going to be R squared, and G phi phi, comma 0 is 2A dot R squared sine squared theta. So they're easy to differentiate because these are very simple functions. And this is, so what I could have said was equals 0 except for 183 and what I just wrote in blue on the iPad. Anyway, if you put these things together, you can find, for example, that, and again, I hope I did this one correctly, that gamma I theta theta, these are the Christoffel symbols of the first kind, which are simpler, are all vanish except for GR theta theta, which is minus A squared R. Let me just remind you that what GI theta theta, gamma I theta theta would be, it would be this expression, but without raising the first index. So it would be 1/2, comma, G so I've got I and L both equal to theta. Well, unfortunately, I've used I for two different things here, but if, oh yes, I'm going, well, this would be GI theta, comma theta, plus, I think it actually comes out to 2 this, and then minus g theta theta, comma 0. And so there's a, what did I do? I switched from I to 0 in that last one. And in particular, then 0, or actually, it's not 0, it's t. So t theta theta then would be 1/2 times 2g t theta, comma theta, minus g theta theta, comma t. Okay, so if I haven't screwed up the indices, this one is certainly 0 because the metric is diagonally. So we just have g theta theta, comma t. And well, I wrote zeros here instead of t's. Oh, my notation. I'm screwing up my notation. This is really GTT. And so all these zeros should be t's. And in any event, one eventually gets that GT, gamma T theta theta is A dot R squared over C squared. I'm sure of this last one, and I think this one is probably right also. But I don't want to, well, let me just remind you of what the formula is. So gamma K IL is 1/2. And now it would be all 3 of these, but it would be G K I comma L plus G K L comma I minus G L I comma K. So that's what it would, what the Christoffel symbol of the first kind is. And so in particular, G R theta theta, or gamma R theta theta in particular, gamma R theta theta is 1/2. Now, R theta comma theta would vanish because the metric is diagonal. Similarly, the second term vanishes, and so we just get minus G theta theta comma R, and G theta theta comma R is 2 this, and so this is minus minus A squared R. Which is what I wrote down here. Okay, so this is how this works. It may be easier, however, to use the action principle to derive these things. And if you do that, what you're saying is that the action principle says that that the variation of the action of a falling object is 0, and you do small changes of these parameters, and one then finds that in particular, this thing here is related to gamma TRR, and similarly, this one is related to T theta theta and T phi phi. And so what you do is you have to compare this to what the variation is in terms of the Christoffel symbols, and that's back in an earlier section. And so you find that these are the values. In a similar way, if you vary R, you get these, and if you vary theta of tau, you get these, vary phi of tau, you get these. To tell you the truth, whether this is actually simpler, I don't know. It certainly requires more thought, but on the other hand, the other requires keeping track of so many indices that it can be very confusing, as you've just seen. I got confused. The Ricci tensor, our formulas were that, for example, R00 is a trace of the curvature tensor like this, and the curvature tensor can be written as a commutator of two covariant derivatives in a certain form. Let me just say that if you struggle through all this, you eventually find that the RR components of the Ricci tensor are this, the theta ones are this, the phi ones are this, and the Ricci scalar is this. R00 was obtained up here, and it turns out to be minus 3a double dot over a. You then sum these with the inverse metric tensor, and you get the Riemann scalar. It turns out, of course, that there is a Mathematica script that does this. There is probably a MATLAB script out there somewhere that does these same things. And let me sort of write down, I will look for it tonight, MATLAB script. There probably is one somewhere. Anyway, for the Mathematica script, it's very convenient. What you do is you just put in what your metric is. First, you put in what your coordinates are, then you put in what your metric is, and then boom, it computes everything. And you might say, well, how can it do that? Well, these are very simple rules. All you do is differentiate and multiply, and it's all mathematically very simple. It's just that there are 4 indices that take 4 values, and so things can get, from the human point of view, very complicated very fast, and very tricky and very error prone. On the other hand, that's exactly what computers are good at, keeping track of simple things. The Friedmann equations. Well, first of all, of course, the Einstein equations relate the two tensors, namely the Ricci tensor and the Riemann scalar, to the energy momentum tensor. So to do cosmology, what you have to do is you have to figure out what the energy momentum tensor is. And the energy momentum tensor, it turns out that one introduces simplifying assumptions to make this a practical calculation. Are these assumptions a little too simple? Well, they may be, but they're the standard assumptions, namely that the universe can be described from the point of the Big Bang on as a perfect fluid with a 4 velocity. And remember, the 4 velocity looks like this. The energy momentum tensor then is the pressure times the metric plus the product of the 4 velocities times this combination of rho plus p over c squared. But we're using co-moving coordinates. In other words, our coordinates r and theta and phi are coordinates in the universe which in which the expansion of the universe is accounted for simply in the scale factor A of t. And so in these co-moving coordinates, the 4-vector velocity is just 1, 0, 0, 0. So then when you compute TIK, you get this very simple matrix. And the trace of the matrix is just minus c squared rho plus 3p. And so it's a simple expression here. Rho, I should mention, is the mass density. So when we put all this together, what we get is that A double dot over A is minus 4 pi g over 3 rho plus 3p over c squared. So this is from this expression here. And this looks like a very simple equation, but it's a little more complicated than it looks, because you see rho and p depend upon A. And so one has to straighten that out. The Einstein formula for the scalar curvature is just R is proportional to the trace of the energy momentum tensor. And so putting that into this, what we get is A double dot over A plus A dot over A squared plus this equals, and then the energy momentum part gives us this expression here. And using this equation, we can eliminate the second derivative. In other words, we just substitute for that expression there. And then when we rationalize things, what we get is one of the Friedmann equations. So the Friedmann equations are this equation and this one. This is the one that is most useful, though, because it is first order in time. And this tells us then that the square of the Hubble rate is the mass density times a constant minus something that depends upon the geometry. And it's k over L squared, A squared times C squared. And in reality, when we haven't, with at least last time I looked, which was, I guess, a few months ago, it was impossible to see any sign of this term because L squared is so big. The left-hand side, as I said, is the Hubble rate, A dot over A, and the Hubble rate at the present, or the Hubble frequency at the present time, is called the Hubble constant. So this, like so many things in astronomy, is a misnomer, an abuse of language, because the Hubble constant, which is the present value of the Hubble rate, changes from day to day, and so it's not a constant at all. In terms of the Hubble frequency, the first order Friedmann equation can be rewritten as h squared is the mass density minus this geometrical factor. And one important special case, which is of great practical importance, because as I said, one sees no sign of this term in present astronomical observations. And so the universe that in a perfectly flat, if we set k equal to 0 and describe a perfectly flat universe, then in a perfectly flat universe, the mass density has to have a certain value, and that's called the critical density. So the critical density is the one in which this equation is true for k equal to 0. And so that means that the critical density is 3h squared over 8 pi g. And so that's given by this expression here. And now if we divide the Friedmann equation, first order Friedmann equation, by rho sub c, what we get is this formula here, which looks like a stupid formula, but it's actually very important. What it says is, on the left-hand side is something that is positive for k greater than 0, 0 for k equal to 0, and negative if k is less than 0. And by the way, traditionally, one sets k equal to +1, 0, or -1. I should have mentioned that earlier. It's said, text says so, but I forgot to mention it. And so what this tells us is that if k is +1 or positive, then what's true? This thing is positive, so rho has to be greater than rho c. Rho over rho c is something that astrophysicists have been calling omega for the last 20 or, well, last 40 years. They've been calling it omega. So this is omega then is rho over the mass density over the critical mass density. And when I say mass density, I'm including the mass density of radiation, the mass density of dark matter, the mass density of dark energy. It's the total mass density. In other words, it's the energy density divided by c squared. So it's kind of silly to be using it, but that's what one does traditionally. And what this says then is the ratio of the mass density to the critical mass density is greater than 1 if the universe is closed, and that means omega is greater than 1. If in a flat universe, k is 0, in which case rho equals rho c, and that's how we got to rho c after all. And that's the case for omega exactly equal to 1. And then for an open universe, what you have is k is negative, rho mass density is less than critical, and omega is less than 1. Now, as far as we know, omega is 1. Okay, now density and pressure. The vanishing of the covariant derivative of the energy momentum tensor is this expression here. So the energy momentum tensor vanishes. That follows from the principle of least action. That gives us this equation. We now substitute for, we now specialize to the case of a perfect fluid, and we're in the rest frame of the fluid, and consequently, this expression simplifies enormously, and it gives us that, in particular, that the time derivative of t00 plus these other terms, which one can then compute, and it gives us eventually 0 is the time derivative of the mass density plus the Hubble constant, or the Hubble rate, I should say, times rho plus p over c squared. And so that's, of course, a very important equation. This is effectively conservation of energy. It also follows from Friedmann's equations. So what you get is that rho dot is given by this, and that's the same thing as saying that that d rho dA is minus 3 over a rho plus p over c squared. Now, this mass density is composed of fractions, each contributing its own partial pressure. And so what people have done to straighten this out and to make it, to make sense of these equations, simplify them, one writes p sub I as c squared times the mass density of the ith component times wi, which is, and wi is the is how the ith mass density is related to the ith pressure. And putting those together, what we get is d rho I dA is given by this, and you can then integrate that, and you find that rho I is just a constant times 1 over A raised to the power 3 times 1 plus WI. And so this is then, this is the utility of that. We see how each rho I depends upon each mass density depends upon the scale factor, but in a different way, depending upon the nature of the mass density. And there are basically 3 really important cases. The first is, sorry about that. The first is the simple picture, or the traditional image of the universe as being nothing but a bunch of stars that don't interact except gravitationally. And then the pressure is 0. And so what you want then is that W is 0. If W is 0, then rho is some constant, and then it goes as A0 over A just to the power 3. Well, that's what we could have surmised or realized without going through all this analysis, because obviously if the universe is just a bunch of stars and the universe is expanding, then the mass density will drop with the as the scale factor expands, because density is 1 over volume, and volume rises as A cubed. With radiation, it turns out that W is a third, and the reason for that is that the radiation decreases, first of all, as 1 over A cubed because the volume is expanding, but then as an extra factor of 1 over A, because as the universe expands, the wavelengths expand, and so the momentum drops, and so the energy density, or equivalently the mass density of radiation, goes down as the 4th power of the scale factor. On the other hand, dark energy, as far as we know, or let us say we put it in, I mean, to really what's going on is a great deal of ignorance being dressed up as theoretical physics. The fact is, we don't know anything about dark energy. All we know is that basically what Adam Rees and Saul Perlmutter and their groups and others have shown us by measuring supernovas at very large distances, namely that the universe is expanding, and the acceleration of the expansion of the universe is accelerating, but those measurements are not so great. And so how fast is it in accelerating? Is the acceleration constant? Is this actually a constant, or does it vary with space and with time? We don't really know. And so we just put it in as a constant, and that's fine. That simplifies the equations and means we can then compute things and compare with astronomy, but we don't really know that. I mean, there could be a term that's 1 over A squared, another term that's 1 over A, and it could be a term that's 1 over log A. I mean, you just don't know. So this is a simplifying assumption. We don't really know what's going on. In any event, what one does is one takes this and substitutes it in here, and this is then allows one to compute something. And so here we have A dot over A squared, which is the square of the Hubble frequency, is the mass density, which is these terms in our simple model, and then a geometrical factor. And the basic picture that we have is that there was a period of inflation in which was essentially instantaneous, when a quantum fluctuation went to the size of a basketball in an instant. And once it was the size of a basketball, it then expanded according to ordinary general relativity. Of course, the expansion is from a quantum fluctuation to a basketball size is also supposed to be consistent with general relativity. It's just that during that superluminary expansion, the expansion of space was driven by an absurdly high potential energy density of one or more scalar fields. That's the picture. Whether it's true or not, we don't know, and it could have been that there was a prior universe that collapsed and bounced. So we don't really know. What we do know is the universe was super hot. It was so hot for 380,000 years that most of the hydrogen was ionized, and it was only after that hydrogen became atomic hydrogen as opposed to protons and electrons that the universe became transparent. So the moment of transparency was 380,000 years after the Big Bang. Then there was a period before the hydrogen collapsed gravitationally enough to form stars. And then once the stars formed, they then reionized a lot of the hydrogen. And so we have a lot of ionized hydrogen. We have also hydrogen and helium gas, and we have stars and galaxies and black holes and so forth. And this then expanded according to general relativity. And around 4 billion years ago, the expansion started to accelerate in a detectable way, and that's what we call dark energy. In any event, if we divide the Friedmann equation by the square of the Hubble constant, we get this expression here. And now what we can do is notice that H0 is related to the critical density, and so we have the critical H0 squared is related to the critical density. So we have ratios of densities to critical densities and scale factors. And so this is omega lambda, this is omega matter, this is omega radiation, and then this can be thought of as omega geometry if you want. The Planck collaboration have done remarkable work analyzing this, and what they've shown is that what they've assumed is that the universe is composed of matter, and only about 19% of the matter is actually baryons. The rest is dark matter. The idea of dark matter is particles with masses. Particles, first of all, they're dark in the sense that they're transparent. They don't interact with photons, or at least not in any detectable way. And the idea is that they're cold in the sense that they were heavy enough to be non-relativistic when the universe was about a year old. Well, of course, when the universe was a year old, it was very, very hot. And so these have to be particles with masses in excess of keV. Of course, the energy density of the cosmological constant is what we call dark energy. And so the Planck collaboration put in these assumptions that omega lambda is about 0.7, omega matter about 0.3, most of it dark, most of it transparent. And this they took to be, well, undetectable, and so they put in a small positive value, but with an uncertainty that's vastly, much greater than the 5 times greater than the value. What they then did was they got an estimate of the Hubble constant of being 67 or, well, 68 basically kilometers per second per megaparsec, megaparsec being a perfectly absurd number. The present Hubble frequency then is 2.2 10 to the minus 18 inverse seconds. So it's very high. I'm sorry, very low frequency, 10 to the minus 18 seconds per second. The Reese group and other groups use the Gaia Observatory. They calibrate Cepheid variable stars and type 1A supernovas, and they use these as standard candles to measure distances. They get something like 73 kilometers per second per megaparsec. Or if they put in these measurements from the tip of the red giant, they get, well, again, they get 73, but it's 72.53. The uncertainty is of the order of 1. But even though both of these have uncertainties, the uncertainties don't overlap at all. And so we've got something like a 5 sigma, 5 sigmas to be explained. And the astronomers at Reese's group think that that the difference between the Planck value for the Hubble constant and the astronomy value for the Hubble constant are so different that it can't be statistical errors, that there must be new physics. And of course, that's very exciting. With luck, we'll figure this out. I'm sure we don't have nuclear war because of the military-industrial complex and the stupidity of our government. If we avoid nuclear war, then people will figure this out in 5, 10, 20 years with better measurements and so forth. There's another problem, namely the amplitude of matter fluctuations on a scale of 37 million light years, or 8 over h megaparsecs. This is a discrepancy of 2 to 3 sigma, so it's not yet serious. It's could well be just bad measurements. By the way, this h, which I should have probably written in italics, this h is, in other words, it's defined this way. H zero rather is h times 100 kilometers per second per megaparsec. So so h is about 3/4 or 0.7, let us say, if we compromise between these two values. H is in the order of 0.7. That's a notation that's used a great deal. So let me take you through some of these computations here. First of all, the radiation density we can actually measure, because one can, most of this energy of radiation is the black body radiation, which of course was only discovered in the 1960s, around 1965 or so. And you know the story. It was electrical engineers were trying to build better radio telescopes for Bell Labs, which was then doing independent research before the government destroyed AT&T. What they found was a lot of static in their radio telescope, and they didn't think of it as a telescope. They just thought of it as a sensitive radio antenna for communications and telephone radio communications. And they heard this hiss, and they did everything to check the electronics, and then they thought it was pigeons. And they got rid of the pigeons eventually, and it was still there. And eventually they decided that it was real, and they were in Princeton, New Jersey, and so nearby was Princeton's physics department, in which various theorists and experimentalists were thinking about the Big Bang and realizing that there should be some noise left over, radio noise left over from the Big Bang, and so they realized it was cosmic microwave background radiation. Anyway, that's most of the radiation density of the universe. And the temperature, you can measure the temperature, of course, very easily of these photons. In fact, they're the best black body that's ever been measured. And you then find an equivalent. You just use the Planck distribution to find the energy density as it goes as present temperature of the 2.7255 raised to the fourth power times various constants, and that gives us a formula 5 10 to the minus 31 kilograms per cubic meter. Those are I'm using MKSA units throughout the book. Then you add in neutrinos and antineutrinos, and they're at a somewhat lower temperature, though, because they decoupled before the positrons annihilated with electrons. And so our photons have the CMB photons have the energy of positron-electron annihilation, whereas the neutrinos don't. And so when you add them in, there are 3 different kinds, and then there are some geometrical factors that have to do with the way the Planck distribution changes when you go to fermions, and in particular, spin 1/2 fermions. You get these factors. And so adding the neutrinos to the photons, you essentially double the thing, or almost double it. And no, actually, you do essentially double it. So you get, instead of 4.6, what am I doing? Anyway, it's something like doubling it. And if you divide by the critical density, then you get an expression that's basically 10 to the minus 4 for radiation. So that's this constant here that we've just computed. This is something you can compute. Well, again, there could be other massless particles that we don't know about. So there could be another factor here. But doing the best we can, we put in our value for dark matter. We put in a tiny value that could be basically ignored, and then we put in our value omega lambda, all coming from over here. And what we then do is we take this equation here, and this equation, maybe I'll switch to red. It is a dot squared over a squared is equal to these various omegas. And so it's omega plus, now omega 0 is the one at the present time. So there is some utility. I've got to admit that the geometrical one goes as 1 over a squared, and then you get omega matter over a cubed plus omega radiation over a to the fourth. So this is our equation, and then you get a dot squared then is omega lambda times a squared plus omega geometry plus omega matter over a plus omega radiation over a squared. So that's the equation that one has. And you then say, well, a dot is dA dt, and so you can rewrite that as dA over well, what one writes it as this over A times H, and that's of course because this is dA over A dA dt. So that's how you get from there to there. And so this thing in the bottom is H0 is 1 over H0, or 1 over, well, then this is 1 over H dA over A, and then you rewrite this as 1 over H0 times H0 over H dA over A. And so eventually then you get dt. Well, if you set x equal to a over a0, actually, I think this was a big mistake. I was following Weinberg here, who switched from, instead of taking advantage of the astronomer's notation, he used x as a over a0, but if a0 is 1, then this is just x equal a. I think I'm going to have to change that. In any event, one gets this expression here that gives us the time as a function of scale factor, and it gives us that as an integral 1 over the Hubble constant times an integral here of dA over A. And when you multiply A through here, then you get an A squared, the A squared inverse gets canceled, and you get these two terms. And so you can just do this thing, and I wrote a little program to do it, and use that program then to compute what T of A would be. You get a formula for T of A, you put in A, you do the integral. These guys are constants, you just do the integral. This is, if you assume a given value for the Hubble constant, you then get T of A. And so if we take H0 from observation, and again, there's a 5 sigma error there, but uncertainty, you then get T of A, and if you invert that, you get A of T. And one can also compute the redshift as a function of time, and the redshift here is 1 over A minus 1. So the idea here is that Z is 1 over A minus 1, so this is 1 over A minus A over A, so this is 1 minus A over A. And you might say that's weird, but remember, the astronomers have A equal to 1 at the present. It was always smaller in the past. Anyway, that gives us then Z, and here's Z of T, and what we see here is that at present time, of course, Z is 0 because A is 1, but at earlier times, back at 1 billion years, maybe 500 million years, Z was 10, something like that. So this is just, this curve has nothing to do with the physics. It's just a definition. On the other hand, this is the thing that I computed with doing this integral numerically. And so if we look at what happened in the first 100,000 years, what we had was a period. The first period is called the period of radiation, or the era of radiation, and that lasted about 50,000 years. That's where radiation was, the mass density of radiation was greater than the mass density of, I'm sorry, the energy density of radiation was greater than the energy density of matter, or equivalently, the mass density of radiation was greater than the mass density of matter. And you can see these curves here. Here I'm plotting the energy density, or the mass density of radiation. You see it falls more quickly because it falls as 1/8 to the 4th, whereas the mass density falls as 1/a cubed. And of course, this is T, and that's A, but and here is, this curve then is A of T. And so for this first 50,000 years, you can see that this is going as essentially the square root. Well, let's actually, let me not do it by eye, but rather get, yeah, I was right, it is the square root. So A, the scale factor goes as the square root of T initially, or equivalently, T goes as A squared for the first 50,000 years. And then after that, it, well, we'll get to after that in a moment. So, well, maybe I should just read some of this because it is sort of technical. So, yeah, all right, actually, here's the way to think about it. Basically, the first 50,000 years, we're talking about radiation. And radiation we've seen goes as 1/8 to the 4th. On the other hand, it goes as T to the 4th. So consequently, T goes as inverse A. And that goes then as 1/the square root of the time, or equivalently, the time goes as the square root of, A goes as the square root of time. And in particular, when the temperature was between 10 to the 10th and 10 to the 12th Kelvin, the radiation was mostly electrons, positron, neutrino, and dark matter, but we don't know what dark matter was. By 10 to the, when temperature dropped to 10 to the 9th, the positrons had annihilated with electrons, and but the neutrinos had already fallen out of equilibrium. Between 10 to the 9th and 10 to the 6th, the energy density of non-relativistic particles became relevant. And the time temperature relation is 1.78 seconds times 10 to the 10th over the temperature, and that ratio squared. This I took from Weinberg's book on cosmology. During the first 3 minutes, by the way, that's a very good book, which Weinberg wrote about 50 years ago. It's still, because it was Weinberg who wrote the book, it's still absolutely true and very much worth reading. The only things he didn't know about at the time were dark matter and dark energy, but the story he tells is still basically true. So during the first 3 minutes, the quarks and the gluons formed hadrons. They decayed into protons and neutrons. And the lifetime of a neutron is around 900 seconds. And they form the light elements, hydrogen, deuterium, and helium. And this is called Big Bang nucleosynthesis. The density of non-relativistic matter falls as 1/a cubed, and this then gives us how things go in. So let me describe. This is most of the last 14 billion years, and what one has is something that looks kind of linear to my eye, but right. So let's go to the next part. The era of matter started after the era of radiation. It started at about 50,000 years, and it lasted until it lasted essentially for 10 billion years. And during this period, A is not linear with time, but it almost is. It's A is T to the 2/3. And on the other hand, once we get past, once the universe was 10 billion years old, the most important factor was the dark energy became important, and 10 billion years ago it started to importantly accelerate the expansion of the universe. And so if we look at the universe on a scale factor, on a scale of 50 billion years, what we see is here we have where this is, so to speak, the inflection point here at 10 billion years, and then dark energy really takes over at about 20 or 30 billion years, and then you see essentially a pure exponential there. And so 10 billion is when the two energy densities, dark energy and matter, are equal. And now, how is it that things what's the equation for the dark energy era? Well, it's basically the second order Friedmann equation, and then we just have a constant over here, and the big constant. You see, rho sub lambda is a constant. Rho matter becomes insignificant. Rho radiation even more insignificant, because they go as 1/a cubed, 1/a to the 4th. And so one has this expression here. And if you ignore these two, you simply get an exponential. You get that A of T is the Hubble constant, the square root of the energy density times the time times the scale factor. And so this expands exponentially, and and basically that's the indefinite future of the universe. Unless there's something we don't know about, the universe goes on expanding forever. And I remember an article Weinberg wrote, which is that he imagined what people living on Earth would see 30 or 40 billion years from now, and they'd look out, and they might not even be able to see the stars, or at least they'd see very few stars. in the limit, you wouldn't see any stars. You'd just, of course, I made a mistake here saying that because in 30 or 40 billion years, the sun would have radically changed and probably burned up the Earth as it became a red giant. And so people would have to use one of Elon Musk's spaceships to get off to another planet somewhere. By the way, this moving into space is not as crazy as one thinks. Obviously, if you tried to do it in spaceships, you'd need a great many spaceships to move 7, 8, 9 billion people. On the other hand, if what you constructed in space was a sphere and you just got it up into space in a region that was so that the acceleration of gravity was negligible. And there is this possibility of a space elevator, by the way. And so this is not totally impractical. So you could then have what you might think of as a city in space, in which you'd use a three-dimensional volume, essentially gravity-free, but with air, of course, duh. And it turns out that the volume, you see, we don't really use the Earth. All we use is the bottom 100 feet of the atmosphere. And in Albuquerque, it's basically the bottom 20 feet of the atmosphere. And so people would it would be extraordinarily dense. It would make China look like Nevada. But one could have plenty of room for the whole population in a sphere with a radius of maybe 50 kilometers or 100 kilometers. And on the surface there, one would use solar energy to grow plants. And it's not totally out of the question. And moving that to another planet would be a big deal, but just having it float in space, not far from the sun, far enough to be safe, would be, I think, quite practical. Well, I shouldn't say quite practical. It's plausible. It's imaginable there, because I imagined it. But whether it's possible and how practical, it's another matter. Well, never mind this future business. What about before the Big Bang? Well, what we just got through here was to analyze this equation when we ignore these two terms and we just have a constant here. Well, that is thought to be what happened before the Big Bang. Before the Big Bang, the idea is that some one or more scalar fields got to, by chance, fluctuated to a value that was just absurdly high, and its potential energy, consequently, was just enormously high. And so in a tiny volume of space, you had a very high energy density. Well, that's equivalent to saying that you have an omega lambda, or you have a rho here, that in a tiny volume, this rho is absolutely stupendously huge, in which case you get exponential expansion. And so the idea was there was an exponential expansion, and when you have an exponential expansion at an extraordinary rate, you don't need very much time to get to a macroscopic size. And so the idea is that a quantum fluctuation occurred in a volume that was entirely microscopic, and then in a time that was virtually instantaneous, that microscopic volume expanded to a macroscopic size, in other words, this big. And by the time in that instant that it expanded to be this big, by the time it got this big, the scalar field got back down to its normal value, but then all this energy was released. That was the Big Bang, when all that potential energy turned into radiation of all kinds. And of course, it was radiation of all kinds of particles that we don't even know about, and they then became dark matter, dark energy, radiation. Well, the dark energy part I shouldn't have said, because the dark energy is thought to be the energy density of empty space. And what we're talking about here when you had a period of inflation, an instant of inflation, and then all that incredible potential energy density of a volume the size of a basketball went to radiation, and that was the Big Bang. And the universe has been expanding ever since. So that's now what was before that? Well, that's inflation, and then there's the possibility that that the universe, here's the formula. Rho is the energy density, 8 pi g rho over 3. That gives us the rate of expansion, and this rho here is whatever the potential energy happened to be. So in other words, rho might equal 5 to the 4th or something like that, and and with a coupling constant g that might be big anyway. The other possibility has been advanced by Steinhardt and others, namely that it wasn't a quantum fluctuation, it was that the universe was always existed, always was big, and then it collapsed and formed a Big Bang and re-expanded. And of course, one could go beyond that and say, well, the universe isn't homogeneous at all. There are all these places that some are expanding, others are contracting, and you have Big Bangs all over the place. And another possibility, in fact, I remember being at dinner with some theorists 50 years ago when we were talking about the possibility of a quantum fluctuation creating the universe. And we looked around the table and said, well, there's a possibility of another quantum fluctuation somewhere in this restaurant or somewhere else on planet Earth. And that would then create another universe that would be inside ours and so forth. And Sidney Coleman actually worried about that, or thought about that, and computed how fast it, anyway, the signal comes basically at the speed of light, and I think when it hits us, it's bad news. Makes nuclear war look like a tea party. All right, well, we're kind of out of time, and pretty much done with this, with the chapter on relativity. I may say more about relativity tomorrow, do some examples, but we have 2 more class periods and an exam. Instead of an exam, I'm just going to give a lecture, and the grading's going to be based just on homework. And I think in the next 3 lectures then, I'm going to say some things about other things. And there's some very low-hanging theoretical fruit that's that you should grab and understand. And some of it's group theory, some of it's statistical physics, some of it's path integration. And maybe I could, in 3 lectures, give you low-hanging fruit, not the details. Anyway, well, we'll see. Let me take a look at the chat screen to see if there's been some important message. No message at all. Okay, so I'm going to stop recording now, stop sharing. I wish you all a good night, and I'll look forward to seeing or to being with you tomorrow evening. Bye.